I think maybe it's great if we found out where this Pythagorean identity came from. It's a proof of the sine squared of theta plus the cosine squared of theta equals 1. And it's actually a really simple proof to construct. So first, we're going to have to draw a circle. That's what I'll do first. That's my y-axis. And I'm just only going to draw the first quadrant of this circle. It's going to be centered at the origin. Alright, that's close enough. Best I can do. That's going to be a circle of equation x squared plus y squared equals r squared. And now I'm just going to pick an arbitrary point on the circle. Let's call that point P, x comma y. And I'll drop a perpendicular down to the x-axis here. And draw a line segment from the origin all the way to that point. And I'm just going to call this theta. That's the right angle. And if you know from your circles and geometry and stuff, the x-coordinate is obviously x, and this is y. So, what's the sine of theta? Well, it's just going to be, I forgot this is also hypotenuse r, by definition of our circle. The sine of theta is going to be opposite over hypotenuse, y over r. And the cosine is going to be x over r. You're adjacent over your hypotenuse. Now, if we want to solve for the variables in the numerator, the y and x in this case, we can just multiply the bottom, actually multiply both sides of each equation by r. So we'll just do that right now. If I multiply both sides by r, let me draw a line there. I'll just put parentheses here and just multiply that by r. We get r times the sine of theta equals y, and r times the cosine of theta equals x. And you're going to see these a lot in your trigonometry classes, because they'll be helpful when you go from polar to rectangular coordinates and everything else like that. Well, we solve for x and y, and we can now go ahead and just put that into our circle equation. So we'll have the quantity r times the cosine of theta squared out plus r times sine of theta quantity squared, and that's going to be equal to r squared. All I did here was just substituted x and y from what we got. And now we're going to expand this. So I'll just write out the multiplication so you can see it's just going to be r cosine theta times r cosine theta plus r sine theta. I forgot to put parentheses. R sine theta times r sine theta. It's equal to r squared. Now we can just multiply it through. We have an r squared plus cosine squared theta. And if you've never seen this before, it's just alternate notation for the cosine theta quantity squared. And that means you're squaring the ratio itself, not squaring the angle. So back to reality. We have r squared cosine squared theta plus r squared sine squared theta equal to r squared. And now we can just divide through by r squared. And we have cosine squared theta plus sine squared theta equals 1. It was actually pretty easy to do, wasn't it? And that's a fundamental thing. It's one of the identities you'll learn. There's also many identities that you can generate from this. I think I should take the time to do some of those. Let me erase some of this stuff. So we have cosine squared of theta plus sine squared of theta equals 1. If we divide it through by the cosine of theta, cosine squared actually, you generate a new identity. Cosine squared theta divided by itself is 1. The sine squared of theta over the cosine squared of theta, that's the tangent squared of theta. And then 1 over the cosine squared is the secant squared. And you can also generate, let's erase this stuff up top here since we already have the proof done. We also generate another proof by going through the same thing, except instead of dividing through by the cosine squared of theta, you divide through by the sine squared of theta. The cosine squared over the sine squared is the cotangent squared. Sine squared divided by itself is 1. 1 over the sine squared is the cosecant squared. So in a matter of 6.5 minutes, we managed to get all 3 of the basic Pythagorean identities done just by using the definition of the circle.